pleased to introduce Adriana Salerno and Ursula Whichter. They're going to tell us about zeta functions, point counting, and mirror symmetry.
Hello, everyone. We have a short talk this afternoon, so we decided that we were going to just tell you all about an interesting example. And it's an example that I think some people in the audience will know very well, and some people will hopefully find novel and surprising. So this comes out of the work of Philip and Xenia, who are in the audience, and also Fernando Rodriguez-Villegas. And the general topic here is arithmetic mirror symmetry. Mirror symmetry is this prediction that there should be pairs of varieties that have certain linked properties despite being not at all isomorphic. And one of the things that you can do with this pairing is you can actually make some conjectures about the number of points on each variety, or some arithmetic properties on each variety that should somehow be related. So let's do just the sort of very quick high-level intro to mirror symmetry for people who have not thought about it much before. This is coming out of string theory, which is an attempt to combine Einstein's theory of relativity with more of quantum physics. And so what we need here is really a sort of relativistic attitude. We've got space-time, which you live in. You probably are perfectly happy believing in 3 dimensions of space and 1 dimension of time. But in order to make string theory mathematically consistent, you need to assume that there are these extra dimensions in the universe. And these extra dimensions are compact. They're not something that we can sense because we usually think of them as being curled up on each other and so small that unless you are a sub microscopic particle, like say a string, you can't access them. And then typically we assume that they have some nice mathematical properties, in particular the complex manifolds. If you're doing serious physics, you should probably assume that it's a 3-dimensional complex manifold, because that gives us 10 dimensions in all. And at this point, if this was really a popular talk, someone would raise their hand and be like, but I heard it was 22 dimensions. But 10 for us, really. And then we want this extra variety to be a Calabi-Yau manifold. So your sort of basic, most physicsy examples are always Calabi-Yau threefolds, and then of course, because we're mathematicians, we like to think about elliptic curves and K3 surfaces, and maybe the 4-folds after the 3-folds, and sort of build this tower of possible examples that you could study with some of this data. So a very, very, very silly way of thinking about it is that at some point when you're setting up a string theory, you need to choose some sections of some vector bundles. And you have a choice between whether you're going to work with a variable and its complex, and the complex conjugate of another variable, or whether you're just going to work with 2 bundles that are nice on themselves. And this is a very, very arbitrary choice, but it sets up 2 different sorts of string theory. And when you work that all out, you have these 2 different theories. They're both perfectly consistent physical theories. They depend on this incredibly arbitrary choice of how you were going to define your bundle. There's no particular reason that you should prefer one over the other, but they seem to correspond to different varieties. And so the prediction that was made is that maybe there are actually pairs of varieties, and we could take either one of these varieties, tack it on as the extra compact dimensions of our universe, and have the same physics that we observe. So this came out of physics. It was all physics for a while, and then mathematicians heard about this, and they had no idea that there should be these relationships between these 2 varieties which are not isomorphic. They didn't have any apparent mathematical relationship until this was pointed out. And so your sort of mathematical view of this whole story is that there are maybe paired families of varieties, one on each side, and that the physical correspondence to having the same observable data should correspond to some sort of duality in the geometric properties. So this is the kind of physicsy motivation that we start with, that we have these pairs either of varieties or of families of varieties. And we're trying to figure out how much that duality can be traced down to a more explicitly number theoretic level. So I want to show you a specific example. This is maybe one of the oldest sorts of examples of what mirror symmetry could be, only because I'm a K3 surfaces person, I'm going to do this with smooth quartics and P3 instead of the very, very oldest example of mirror symmetry, which would be smooth quintics and P4. So let's start with all of the smooth quartics in P3. We know there are lots of them. Generically, each one has a nice element of the Picard group. It's just the hyperplane class that you might slice your K3 with. And then within that family, we can take this family, which is generically smooth. It's known as the Dwork pencil or the Fermat pencil, depending on what kind of mathematics you do. I think the more number theory you do, the more you want to associate Dwork's name with this family. And here, this family has lots of symmetry. In particular, we can multiply any of the coordinates x, y, z, or w by a fourth root of unity. But then if we want to fix an element of the family, we should assume that each of the fourth roots of unity that we choose multiply together to give us 1. So that cuts down our possible number of fourth roots of unity by 1. And then we're working in projective space, so we cut down our fourth roots of unity again because of the overall projective thing. If we multiplied everything by the same fourth root of unity, that wouldn't do anything. And so what we're left with is an action of z mod 4 z squared. And I add a battery already? Oh, right. So then we can take our pencil, we can mod out by this group. When we do that, we'll pick up some singularities. We'll have to figure out how to resolve those singularities. That might involve some choices, but we get varieties that should be isomorphic at least. And then we'll get a new variety, which is itself a K3 surface, but it's a different K3 surface. It's got all of these extra algebraic curves that we threw in by resolving all of these different singularities. So here we are with a new variety. And we think of this new one-parameter family of varieties, the y's, that we got by modding out and doing a resolution, as being the mirror family corresponding to all of the smooth quartics in P3. So these families are very different sizes. One of them has lots and lots and lots of possible complex parameters. The other one is naturally only a one complex parameter family. On the other hand, if you felt like equipping your varieties with Kähler classes, we would have lots and lots of choices for Kähler classes over on the y side, and not nearly as many choices on the other side. So we have this sort of duality in terms of the amount of information we have on each side of this story. All right. And let's just talk about cohomology. If I were feeling really super physicsy, I could write down a Picard-Fuchs equation and I could use it to define some sort of mirror map that I would use to identify certain moduli spaces of each of my families. Here I want to just focus on the Picard-Fuchs equation itself. And in order to do that, I need some way to get my hands on cohomology. In this case, you can do it in a very computationally friendly way. We can represent forms in the middle cohomology of our variety using forms in the complement of our variety that have poles along the variety. And then we have a residue map that maps a form on the complement into the space itself. So this works for a hypersurface and projective space. And then there's this old method for figuring out, I want to find, I've got a period here. I'm just integrating my form over some kind of nice cycle. And I want to figure out what the differential equation is that's satisfied by this period. And you say to yourself, well, gosh, I'm living in cohomology here. I've got my form that lives in cohomology. My cohomology is a finite dimensional vector space. If I go on taking enough derivatives, I must eventually have some sort of relationship. Now, convincing yourself that you can actually take a derivative like this where you're integrating over some cycle, you really strictly have to choose a flat family of cycles and be careful about what you're doing, and convince yourself that it's legitimate to move the ddt under the integral sign. So there's lots and lots of work here, but it does boil down to something that looks remarkably like your quotient rule that you learn in Calculus 1 once you've justified it all. Okay. And then I was saying earlier, we're working in a finite dimensional vector space. We ended up just having different residues of different classes. If we end up with enough of these things, there's got to be a linear dependence between all of our different residues. The one technical detail that you need is, as we take derivatives, the order of our pole goes up. So you do need a formula to compare things that have our hypersurface equation to a higher power with things that, with our hypersurface equation of a lower power. There's a nice algebraic way to do this. You can turn the whole thing into a computation involving ideals. You can feed it to your favorite powerful computer algebra system and make it crunch along on its ideals and work out the Picard-Fuchs equation. And in fact, for the example I just showed you, you don't even need to pull out your computer algebra system. You can organize it very nicely and work it out combinatorially by hand. So you get a differential equation, and it's pretty. I mean, really, what more could you want, right? And in fact, if you make the appropriate change of variables, you get a hypergeometric equation. Now it's Adriana's turn, I think, because she's hypergeometric.
Yes. I'm not personally hypergeometric, but okay. So yeah, so you got this differential equation, and first, before telling you why it's a hypergeometric differential equation, I should say what a hypergeometric function is. So it's just a power series in Z with these coefficients which have a nice combinatorial nature. They're essentially these backwards factorials or these quotients of gamma functions. So the alphas and the betas determine the hypergeometric function, and in fact there's a differential equation associated to these hypergeometric functions, and the alphas and betas also determine that differential equation. And so in fact you can work a little bit with the equation that Ursula showed you, and you can prove that the Picard-Fuchs equation has this solution, which is a hypergeometric function with those parameters at t to the -4. Okay? And so this is nice, and we actually find hypergeometric functions appear very nicely when we're doing Picard-Fuchs equations of families like this. Okay, so back to the Fermat Quartic, we can actually represent every monomial as a 4-tuple, and we can classify them using the action G, or Z mod 4Z squared, and the Griffiths-Dwork derivative. And so this is going to give us a nice way of looking at all the periods at once. And so these are the 3 types of equivalence classes given that classification. And so there's one class of that form. There are 3 classes of this form and 12 classes of this form. So, and the number of classes, of course, depends on how many permutations you can have of each monomial. And so, why is that interesting? We can actually find more Picard-Fuchs equations to understand. And so, the first class is the one associated to the Picard-Fuchs equation that Ursula showed us. But then you can also find, for the 3 classes that I listed second, you get a second-order differential equation for each one. And for the 12 classes, you get a first-order differential equation. And those are also all hypergeometric. So one thing we're interested in is computing zeta functions of mirror families, or mirror pairs of mirror families, right? And so, so if we have X as an algebraic variety, and we denote by the number of points over FQ to the S and S, then we define the zeta function, or the congruent zeta function, by this the exponential sum. And we know the nice Weil conjectures. So the first thing that it is rational was proved by Dwork, and the rest of the Weil conjectures by Deligne. We don't know this, but I'll just say it. And it's not just a rational function, but we can factor out the rational function like this in a very nice way. So if x has complex dimension n, then you have 2n polynomials. The odd-numbered ones on the top and the even-numbered ones on the bottom. And so, and in fact, the degree of each of these polynomials, except for the first one and the last one, is the dimension, or the Betty number, or the dimension of the JS de Rham cohomology. And so, so we can see already that there's this nice relationship between the geometry of our variety and this arithmetic thing that's just counting points over finite fields, essentially. So, this is what we would like to compute for pairs of mirror families. And so Zania, sitting there, and Shabnam Kadir computed the zeta function of the Fermat quartic. And so you can write it like this, where the last polynomial is actually factored like this. And this is why we wanted to talk about these classes of monomials, because there's a factor for each class. And there's 3 factors, factor for each class where there's 3 that are identical and then 12 that are identical. And so then we just need to compute that, and this is what they look like. So I don't like reading equations, but you can see this. And so we know exactly how this factors out, and then the a sub t's, I forget if they had to be something mod p. I don't know if they're, well, anyway, so this is how they factor out. And so there's something, again, linking these periods and these equivalent classes of monomials to factors of our zeta function. And then for the mirror, Zania and Shabnam showed that your zeta function is this. So this is the zeta function for the mirror family. So we can see that this factor that corresponded to the periods of the holomorphic form and its derivatives is invariant under mirror symmetry. It appears in both the zeta function of the Fermat quartic and the zeta function of its, or of the mirror family, to all quartics in P3. So, so that's an interesting mirror symmetry fact. And well, this I already said, that you have all of these equivalence classes that correspond to the factors. And actually the orders of the Picard-Fuchs equations are actually the degrees of those polynomials, so that I didn't say. So there's some, we get a lot of information from understanding the cohomology in the Picard-Fuchs equations. And in fact, Kloosterman in 2007 gave a really general explanation of how these zeta functions factor. And this is what, one thing we suggested is, if we can figure out those equivalence classes, like we just said, in general, then you have a nice way of computing or knowing how the zeta function factors out. So that's a fun project. And yeah, he builds on work by Zania, Philip, and Fernando, and then also a paper by Kadir and Yuri. It's Noriko Yuri. So, the interesting thing is that a lot is understood about these Fermat pencils, or like the diagonal things with the monomial deformation. So, one thing we're thinking about is what happens with other less diagonal things. But it's still, Kloosterman gives it a nice formula for how to find the zeta function, but it relies heavily on knowing exactly what the cohomology is. So there's a project. And so another thing we wanted to talk about is how this relates to point counting. So we've only talked about how to compute the zeta function from a cohomology point of view. But what happens when we just count points? And so let's use this notation. N of t is the number of points on xt over fq, and then star is the number of non-zero points. And so we're going to count points on the Fermat pencil and the alternate pencil. Well, we're not doing alternate pencils today, right?
Right.
So just the Fermat pencil. So the relationship between the point count and the Picard-Fuchs equation is that the point count mod p gives you exactly a truncation of that hypergeometric function that showed up from the Picard-Fuchs equation. So, and a lot of things like this happen in general. And so this means truncation between 0 and p minus 1 over 4 minus 1. So you don't get the full series, clearly, because you have mod p, but you do get that part of your hypergeometric function. So, and I think p has to be 1 mod 4 for this to happen also. So, so that is nice. And you can do it a little bit more generally, so we have to talk about Gauss sums. I'm not going to spend too much time on this, except that this is to establish notation. So when I say g of s, I mean that's the Gauss sum with a multiplicative character chi sub s, which means you pick the fixed generator of the character group, and chi sub s is that power of the generator. And we fix an additive character, and then we can denote the Gauss sum like this. So when you see g of s, this is what I mean. And so there are finite field analogues of Gauss sums. We can think, I mean, the Gauss sum is a finite field analog of the gamma function. If you see, e is like, e to the minus c is like the additive character, and d to the x is the multiplicative character, and we have a sum. So it's natural to define a finite field analog of hypergeometric functions. Remember that hypergeometric functions were defined as ratios of gamma functions, so we can define a finite field analog as ratios of Gauss sums. G of a minus something can be thought of as 1 over g of something. So we have, again, some numerator parameters and some denominator parameters, and h is our hypergeometric function defined like this. Katz is the one that defines it like this in his exponential sums book. So if we can count points in terms of Gauss sums, so we have some theorems like by Koblitz and Delsart and Furtado-Vomita that, and they all build on work by Weil, that says that you can write the number of points as in terms of Gauss sums. And so essentially we're writing the number of points in terms of a finite field hypergeometric function instead of a general hypergeometric function. And so you can see if you do this computation, you actually get 1 type of sum, 3 of another type of sums, and 12 of another type of sums. And we've seen this before, and this, in fact, the group action splits up our number of points in a nice way. So the terms all correspond to our equivalence classes of monomials, and each of the sums is an approximation to the solution of the Picard-Fuchs equation for those corresponding monomials. So again, we see this close link. Yeah?
Just wondering, are those formulas just mod p, or are they actual liquid?
No, this is not mod p. This is a finite field count. This is a total count. So if we forget about the number of points when the parameter is 0, then this part, or we can think of n of p of t as a function of t as being some constant plus some hypergeometric functions. If we take this and we mod out by p, we'll see hypergeometric functions come up. But this is the finite field version, so we don't mod out by p here. And in fact, one of the tricks, and the reason we were suggesting the p-adic gamma function, is the Gross-Colas formula tells you how to write Gauss sums in terms of p-adic gamma function. And p-adic gamma functions are amazingly computable. And so if you want to plug this into a computer, you turn it into a p-adic gamma function sum, mod out by an appropriate power of p, because this is an integer, so there's going to be a bound on p's given by the Weil conjecture. And so then we get enough information to know exactly what the point count should be.
It's funny you say that, because I recently was involved in a project going the other way, where the p-adic gamma function was hard to compute, and I was reducing to Gauss sums.
Really? I always think of p-adic gamma function as so friendly, and Gauss sums is so unfriendly. So maybe we should talk and figure out if we can be friends with both of them. But this is sort of the angle that we've been taking when we do the point counting. So, and the interesting thing is to try to use both the geometric part and the point counting part to see what we can say about the mirror symmetry. And so now Ursula will conclude with the famous example.
Right. So we should go up to Threefolds, which is really where this story started. And I should tell the folks in the audience who are not expert where mirror symmetry comes from as just a word. So here's the Hodge Diamond for Calabi-Yau threefold, and I've included in all of the various dualities, including Poincaré duality and the fact that it's a Kähler manifold and so on and so forth. So you can see that there's really only 2 interesting Hodge numbers. There's the H11 Hodge number and there's the H21 Hodge number up to symmetry. Now, one of the consequences of mirror symmetry is that if I've got a mirror pair of Calabi-Yau varieties, then H21 of your first threefold will be H11 of your second threefold and vice versa. And so that means if you compare this Hodge diamond and you look along one of the diagonals, for a mirror pair, you've got just a reflection across the diagonal of the entire Hodge diamond. That's mirror symmetry. Put a mirror in. Now, we can take this back to what we know about zeta functions. And we can tell ourselves, well, if we've got mirror Calabi-Yau threefolds, they've got this interchange of Hodge numbers. Of course, Hodge numbers relate to the Betty numbers by just adding across the rows. And so it must be true that the degrees of the polynomials in the numerator on one side has something to do with the degrees of the polynomials in the denominator on the other side, and vice versa. So to that extent, you can make, just given any mirror Calabi-Yau threefold construction, you can make some kind of prediction about what the zeta function is going to look like on the other side. In particular, there's this other very well-known mirror construction for how you build mirror pairs of Calabi-Yaus that's done using polytopes. And all of the polytope information is encoded in Sage in a nice way. I think Andre's going to tell us about the Sage encoding of polytopes in a couple of days. So we might want to know how to take that polytope construction and study zeta functions in that context. Now, in terms of what's known, if we have pairs of Calabi-Yau threefolds that are living in weighted projective space and the mirrors to possibly weighted projective space, then the zeta functions are going to have a common factor showing up. It'll be very, very similar to the story we told you about the Quartics, except now the factor will be in the denominator on one side and in the numerator on the other side, and so we'll see this moving around in the common factor. You can try to study that, not just writing it using these special pencils in projective space or weighted projective space, but using some more of the data that you get out of polytopes. In particular, you can use lattice points in reflexive simplices to organize all of the computations you would do to study this in a nice way. But in the more general toric setting where you've got a pair of reflexive polytopes, what that typically spits out for you is not a spot-on pair of varieties where you can say this variety is precisely the mirror to this variety. Instead, it spits you out more of a pair of families, where you know that there's a familial relationship between all of the threefolds on one side and all of the threefolds on the other side. And so in that setting, it's not as clear whether you should expect the same sort of common factor or not. So one of the things that I have in my list of ambitions is to do just a bunch of experiments where you choose special subfamilies of the threefolds that you, or maybe K3 is just for computational ease, that you get from reflexive polytopes, and see if there's some nice symmetric way to pick up some kind of deeper relationship between the zeta functions than just this interchange in degrees. The other thing that you might want to do is, of course, we've got all of this other data that we have uncovered in our example for the Quartic about the relationship between the Picard-Fuchs equation and the zeta function. So even staying on one side of the mirror relationship, we should be able to take what we know about Picard-Fuchs equations and how it feeds into the whole long story of mirror symmetry, and see what one can extract from that rich data about the structure of the zeta function. This is our ambitions, I suppose, and our rich example, which I think would take a lot more studying to see what the right, most general framework is to set in those examples. So this is where we start.
Are there questions?
I think you already went through the list of things that we should do now.
Yeah. So we have a nice list of little computable things that would get you toward the point of being able to compute more examples. If anybody really likes Picard-Fuchs equations, I can think of things you could try to do in Sage with Picard-Fuchs equations too. We didn't even try to list those.
Yeah. Yeah, I mean, that story that Ursula was telling about the Griffiths-Dwork derivative and how to find the Picard-Fuchs equations, there's a nice algorithmic way to do this, and you can make a computer do it. I tried with the Dwork family, just the monomial deformation where the monomial is that particular one, and you know, but I don't know if they're, of course Kloosterman now has a formula, so it might not be necessary to compute, but if you want to compute Picard-Fuchs equations or the Gauss-Manin connection, you might want to use that strategy, and it's very combinatorial and algorithmic. Yeah.
Maybe I could mention that there's very good code now to compute these Gauss-Manin connections.
Okay,
it's
cool.
code by Sebastian Bankratz in
Cool.
his GitHub account, and it only works over Q, but it can even do the dense cases. So if you take like a degree 4 thing in P3 with the 35 or 31 non-zero coefficients, then it can even compute that. That's
Cool.
very hard to problem, it's very hard to figure out.
Cool.
But there's code for this.
Is it in Sage or is it just in something?
It's currently written in Flint,
Mm.
but I would say this part of the code is quite easy to use.
Mm.
But you will get enormous matrices, like, well, enormous depends on your point of view, but like maybe 25 megabytes,
Yeah.
even over Q with small coefficients as well.
Do you happen to know what the degree of the rational functions will be?
Yeah, so in this example I was just saying a generic one of degree 3 and no, degree 4 in P3, it's like degree 200 more or less. So the denominator of the connection matrix has degree 200 and the numerator a bit more. And that always happens for the dense cases. If you take just a couple of non-zero terms, like here, like for the monomial one, then you get a low degree something. But as soon as you add at least 10 terms, say, then you go to the generic case and you get lots of singular fibers, and it's not very good for these deformation methods. Just wanted to mention that.
Well, I have some not so good code in Paris that does this too.
Because
But-
Sebastian really uses like sparse linear algebra, you have to do very smart things to be able
Yeah.
to compute this.
Should I say that sometimes if you're after the Picard-Fuchs operator, sometimes you can write out a period. You can compute a period to many terms, and then you ask yourself what differential equation does this power series satisfy, and that's often a simple thing to figure out.
Particularly the monomorphic period.
Yeah.
Yeah.
Any other questions or remarks? If not, let's thank our speakers again.